Yeah, hi everyone. My name is Peter. It's my honor to be here today to share with you my research I did last year. I'm a security researcher at Starlab in Singapore, and most of my work focus on hunting vulnerabilities in XNU kernel. And I did found some interesting vulnerabilities last year that I'm gonna share with you guys today. Uh, in the next 30 minutes, I will walk you guys into three parts. The first part, I will share with you some reverse XNU vulnerabilities. And the second one, I will share with you how I develop them further to discover new vulnerabilities. And for the third part, I will share with you the detail of the vulnerabilities found by my further. And for the last few minutes, I will happy to for the Q&A section. Now let's focus on the first part. Now you can see here, let's take a look at the first vulnerabilities. This vulnerabilities was discovered by INB, and this was exploited in various ways. You guys can check it out on the internet, but in this presentation, I just want to focus about the root cause of these vulnerabilities and the lesson learned from that. Now let's look at the root cause of these vulnerabilities. This vulnerabilities is type confused between the k-object field and the sync inheritor field of Mach port. And as you can see here, the k-object field is used to store some kernel object of the Mach port, like IOKit user client, semaphore, and so on. But the sync inheritor port field is specially used in the special reply port, which store the destination of the special reply port send the message to. So in order to trigger these vulnerabilities, first you have to craft a simple Mach message, which the remote port is any kind of Mach port, and the reply port must be a special reply port, and it will trigger the function IPC port link special reply port. And with this ability, it will assign the destination port to the IP sync inheritor port field. And then what happens if you pass this special reply port to the function host request notification port? Like you see here in the reverse XNU kernel, the kernel forgot to check the type of the Mach port, and then it will happy to override the k-object field of this special reply port, which also is the IP sync inheritor port field. And there how the root, and then there's the root cause of these vulnerabilities, and how Apple passed these vulnerabilities. They just add simple checks in this to prevent the further rate of type confusion. Now let's move on to the second one. This second one vulnerabilities is very straightforward and very clear to discover by code auditing. This is recognition in Mach field of the user data element structure in the function user data get value, and this will trigger some kind of user afterfree in the user data element objects. And for more detail of these vulnerabilities, you guys can check it out on the SyncActive website. And then how Apple passed these vulnerabilities, they just simply add the log before increment the Mach field to prevent the recognition. And here is the key takeaway from this part. Firstly, the Mach IPC subsystem has a very huge code path and implement a lot of features which are not easy. And secondly, they use a lot of union keyword in their Mach port structure to store some multiple type of objects. Therefore, it could lead some side effect which cause a very high impact in XNU kernel. And I have a question, how could I create a simple further to discover new vulnerabilities based on my knowledge about reverse? So I came up with the simple idea to create templates, and then with this templates, I will guide my further to explore deeper in the XNU kernel to discover more vulnerabilities. So before going on the detail, here's 3 challenges I faced during develop this further. In order to interact with Mach IPC subsystem, I had to write a simple C program using Mach IPC syscall to interact with it, so that my further had to generate a C file automatically to interact with it, and it's very hard to develop. And the second is the code path of the code base of the Mach IPCs is very huge. And in order to reach some condition, I have to satisfy a lot of condition. And last but not least, mutating the Mach IPC subsystem are not enough to expand the code coverage. Therefore, I have a new idea to solve this very simple. And so what are the template-based further? So the template-based further is basically like a small map you see in this picture. And it also covers some nodes area. And my goal try to expand the map bigger and bigger and cover some unknown area. And hopefully I can find some treasure chests. Yes. So here's my expectation for my further. First, the template further should be easy to modify and edit in C syntax. Since I will generate a test case to a C file, and then compile it and execute it. Secondly, the template should be easy to proc and process in Python to reduce the coding time, so that I will have more time to focus on the targets. And lastly, the template is able to allow me to add some custom function beside the original Mach IPC syscall to reduce the error case and to improve, to fix some code coverage. And then here's my how my further work. So my further receive 2 input. The first input is the prototype test case, which store the information of the function and their argument value. And the second input is the C template. It's basically is the C file, but I added some custom configuration, allowing the further able to read it easily. Now let's move on the prototype test case. So why I choose the prototype test case? Firstly, the prototype is very easy to use in Python. And secondly, by storing my function and argument value in prototype test case structure, it's helped me to easy to mutate those argument value and function. And it's also helped me to write some small tool to try the test case quickly. So how did my prototype test case look like? My prototype test case contains some useful variable to store, such as it will store the number of Mach port will be declared and allocate in the C file, and then it contains an array of the threads, and in each thread is contain an array of the function, and in each function is contain array of argument. And in this prototype test case, I support many types of function argument, allowing the further can correctly read and mutate those value. And here is an symbol of the magnesis structure I define in the prototype. Now let's move to the C template format. The C template format contains some initial definition and some defined variable and function to be mutated. And furthermore, the C template format also supports some attributes allow my mutator to correctly mutate the test case. My C template format consists of three parts. The first part is very simple. It's just JSON strings store some attribute and their value. And the second part is some custom declaration, such as allocate user data Mach port. And the last part is store some signature, allow the further able to fill the C code in. And here is the complete structure of my fuzzer. My fuzzer consists of two parts. The first part is the mutator. Is responsible for mutate the protobuf test case, and then pass this input to the template processor. And in this module is read the C template format, and then combine it with the protobuf test case to generate actual C test case file. So let's focus on the the template processor. My template processor is very simple. I just use regex and replay in Python to do the whole task. So let's focus on the template info part. Each attribute in this JSON string allow the template processor know how to generate the C file. For example, the Mach name attribute is an array of the custom signature. Allow the template processor know the location to fill the C code in. And the port gen function is a list of functions that can allocate a Mach port. And then the blacklist function is the list of functions that will be ignored during the mutation. And the probability function is an attribute store some specific function that I want to have more chance to exist in the C test case. And finally, this is the most important attribute in this part. It stores some custom of the definition of the function and their argument type. For example, here you can see that the function create important vouchers. It has only one argument, and not that the keyword port out means that this function will produce one Mach port as an output. And another keyword beside is voucher IPC is the type of this Mach port. And another example here is the custom send function. It has 5 arguments, but the first 3 arguments are requiring a Mach port as an input. And for the first argument, it requires any kind of Mach port except the MK timer port. Note that the exclamation point before the MK timer keyword means the step. The second argument is require only special reply port as an input, and the last also require any kind of Mach port except the MK timer port plus KObject port plus pset port. So by distinguish the Mach port by type, it will help my mutator correctly mutate the argument to reduce the error cases, and that's increase more chance to read deeper in the kernel. So how did I implement it in Python? First, I just use regex to extract the JSON string, and then I will process those attributes in Python. And after that, I will read the protobuf test case to generate the C code from there. And finally, I will replace the signature I defined in the C template with the C code from previous step. And here is the final output of the C test case. Now let's move to the mutator part. This is the is the host of my fuzzer. It's responsible for mutate the protobuf test case. I implemented 4 mutate strategies. The first, I will mutate the function argument based on their type. I define in the XC templates. And the second, I will mutate the order of calling the function. And for the third, I will mutate the function based on their probabilities point. defined in the C template to increase the hit point of some function I want. And then for the last strategies, I just focus on mutate extract to focus on rate condition case. So how did it look like? For the first strategies, I just simply walk through the definition type I define in the C template, and I wrote I wrote a specific mutation for each type of value, and then I mutate it. And for the second mutating, I just simply randomly swap the order of those function in the product test case. And for the third strategy, is just simply I just extract the waypoint from a specific function I want to have more chain exist in the C file, and then just call the random choose API in Python. And the last mutation is I focus on the mutate the function on the extract. Now my fuzzer is able to run, but how do I know which test case trigger the kernel panics, and how do I save the test case and the kernel panic for analyzing purpose? So I had to write a small script, small Python script, and this script is this script will do two tasks. The first task is act at the TCP server to receive the current test case is being executed by the fuzzer, and the second task is monitor the kernel panic behavior on the virtual machine. So how do I monitor the kernel panics? So it's very simple, thanks to OSX KVM open source projects, which allowing me to run Mac OS on Linux. And it also gives me a lot of useful API to interact with the virtual machine using Python. And furthermore, each virtual machine exposes some serial console, and I can interact with it easily in that directory in Linux. And luckily that the Mac OS kernel also supports some custom boot argument, allowing me to allow me to read the kernel panic structure from the serial console. And here is the sample of the kernel panic structure I read from the serial console port. So in the end, I just wrote about a few lines of code to watch the serial console of each virtual machine to monitor the kernel panic. So I spent over a month to write this, to develop this further. And after that, I spent the whole time for auditing the targets. And I create my own template, my own C template file too. And after that, I ran my further, and it triggered a lot of kernel panic crash. But there are some still valuable crash that I will share with you. The first one I will mention later in the third part. And for the second one, which was part 2 months ago. And this is another interesting case, but because of the time limitation, I will share it later. Now, what is the most important thing for you guys? First, the idea of the fuzzing is the most important factor to discover security vulnerabilities. And the second thing is you have to stick with code auditing beside the fuzzing to improve the mutator. And the last, you have to deep knowledge about the target before fuzzing, and you will find your own security bug. Now, let's move to the third part. And here is the kernel panic structures, my further file. When I and this look a lot of cool structures. And then by the advantage storing the test case in product test case, I can create a very beautiful POC of these vulnerabilities. here. And this POC, in this POC, first I allocate two Mach port. The first Mach port is the temp port and the target port, which has the send and receive right. And after that, I call a function Mach port set attribute with the option Mach port limit info. It will basically set the message queue of this target port to 0. And the purpose of this I will explain later. And for a second Mach port set attribute, I call with another option, Mach port the end request side. With this option, I'm basically allocate the IP request field of this target port with the size I want. And then now move to the custom send. This custom send function I just basically copy from reverse vulnerabilities, and here's how it looks like. It just grab a Mach message with the port descriptor, and I fix the value of the disposition of the port descriptor is Mach message type bool receive. And then let's jump to the root cause of these vulnerabilities. These vulnerabilities exist in the function IPC port request spam. And as you can see here, first it fetch the table from the IP request field. And then there's no bound check-in with the index variable. Not that the index variable is the argument of this function. And then after that, it fetch the IPR entry and there's some checking. And finally, it's all the IPR SORI field of this entry with 1. Before rig, so how did to rig this function? First, you have to satisfy two conditions. The first condition is you have to set the option flag in the Mach message syscall to the Mach send notify. And then you have to, and then the second condition, you have to bypass the IP full macro of the destination port. And in this case, the T port is the target port. And then by setting the message queue of this target port before in the POC, I can able to bypass the second check easily. And then this will rig the function IPC port request spam. And it will receive the I request field of destination entries, which is the IPC entries of the target port. So in the end, we have ability to all-one in the kernel memories, and then to understand deeper of these vulnerabilities, let's take a look deeper in this, and we see the definition of this ID request field in IPC entries header file. And as we can see here, the ID next and ID request field are stored in the same offset, but these fields serve different purpose. So like I said, the union is the problem of this. Now let's move back to the POCs. Let's take a look closer of the first custom send. On this first custom send, I will attack the target port to the as message port, which its disposition is the Mach message smooth receive, and it will rig the function IPC write copy in. And in this case, because this Mach port was allocated with the receive write, so it will rig this case in the function IPC write copy in. And it's basically remove the receive write out of this target port. Now let's focus on the last custom send, which actually trigger the vulnerabilities. And as you can see here, I will grab the Mach message and send it into the target port. And there's some argument that you should notify that the option Mach send notify will satisfy the first condition, and then the sended position of this send box should be Mach message type bool send, and this will rig the function IPC write copy in again. But in this case, because the target port only have one send write left, and this position is move send, so that it will deallocate the entry of the target port in the current IPC table space. Let's take closer up in this function IPC entry dialog, and first it will fetch the index from the Mach port name of the target port, and then it's the reverse, and then it's fetch the IPC entries corresponding with this index, and reverse this entry back to the initialized text. And after that, it will override the INX of this entry with the table INX. And then finally, it will update the table INX with this index. So after that, it continue to read this line in the IPC key-message copy in header. And then at this time, the destination entries were deallocated before, so that the A request field also was modified by the INX field of the IPC table, so that I can control the index effectively using the Mach port name. So how did I do that? I just allocate a lot of Mach port, and then beside this, I extract the index from this Mach port name and compare it with the expected value I want. And when it's reached the value I want, I just rect the loop. And then I deallocate this Mach port to set the table INX field to for one. And finally, I just insert this chunk of code before the POC in the reverse line. And I run in on my iPhone 11 with the iOS 15.6. And I got very beautiful kernel panics. The registry X2 is the index I control, and then the for registry is the pointer of IP request table of the target port. So I found these vulnerabilities around July last year, but during develop the exploitation for these vulnerabilities, Apple quick noticed about these vulnerabilities and quickly released the hot patch on iOS 15.6.1. And here is my key takeaway for this part. So first, Mach port is very complex and it uses a lot of union in their structure, which could lead some side effects. And the last is weak ability to generate custom test case. My further is able to explore more potential code path with haven't reached before. And then here is the end of my third part. So if you guys have any question, I will happy to answer. So thank you guys for listening my presentation.